Hello everyone, my name is Seulki, a PhD student at the University of North Carolina at Chapel Hill. In this talk, I'm going to present our UbiComp 2020 paper titled Intermittent Learning, On-Device Machine Learning on Intermittently Powered System. We envision a future where batteries embedded platforms will be an effective alternative to battery-powered systems. Without a battery, they harvest energy from the environment to a human body, such as the sunlight, kinetic, vibration, and so on. And they are perpetual, maintenance-free, and environment-friendly. For example, an wearable device harvests energy from body heat, an outdoor mobile device harvests energy from the sun, and a heartbeat monitoring system is powered by the human heartbeat. In this paper, we introduced the concept of intermittent learning, which makes energy harvested embedded systems capable of executing lightweight machine learning tasks intermittently. Their ability to run machine learning tasks inside the energy harvesting systems pushes the boundary of battery-based computing, as these devices are able to sense, learn, infer, and evolve over a prolonged lifetime. Two properties of intermittent learning make it unique and a harder problem to solve. First, when energy is scarce, an intermittent learning system needs to decide the best action for that moment so that its overall learning objective is achieved. Second, since not all training examples are equally important to learning, an intermittent learning system should smartly decide to keep or discard examples at runtime, and thus be able to eliminate a large number of unnecessary and energy-wasting training actions. Unfortunately, none of the existing intermittent computing platforms consider these issues, and thus they are not effective in learning when we execute machine learning tasks on them. This animation shows how an intermittent learning system executes a machine learning algorithm with harvested energy. Given a machine learning algorithm, it is first divided into subtasks such as sense, feature extract, and learn, and they are executed intermittently whenever a sufficient amount of energy is harvested. We propose an intermittent learning framework for intermittently powered systems that want to execute an end-to-end machine learning tasks, which involves data acquisition, learning, and inferring. This figure shows a high-level diagram of the proposed framework. There are three main modules corresponding to energy management, machine learning, and task planning. The first one is energy harvester. This module monitors the energy generated by the energy harvester, such as piezoelectric, RF, or solar panels. And it generates an interrupt that triggers an intermittent execution of learning tasks whenever a sufficient amount of energy is generated. The next is learning algorithms. We have developed a library of machine learning algorithms, which contains a specialized implementation of commonly used unsupervised or semi-supervised algorithms for an intermittently powered system, such as k-nearest neighborhood, k-means, and a neural network. These algorithms are split into small pieces of code so that they can be intermittently executed. The last one is dynamic action planner. This module is the heart of the framework, which is responsible for selecting the right action at the right moment in order to advance the learning task toward achieving its desired learning objectives. It contains implementations of intermittently executable method and algorithms to schedule actions, to select what to learn, and to evaluate the progress of an intermittent learner toward task completion. We implement three intermittent learning applications that monitor, learn, and classify air quality indices, human presence, and a vibration pattern. These systems are powered by solar, RF, and piezoelectric harvesters, respectively, and they perform battery-less on-device training, which achieves 81%, 82%, and 76% of classification accuracy. Let's take a look at the air quality monitoring system more closely. The air quality learning system detects and notifies abnormalities in air quality indices such as the UV, ECO2, and TVOC by learning their normal levels on harvested solar energy. Unlike sensing systems that just report the absolute sensing values, it learns the evolving status of air quality and provides environmental context-based notifications, which is smarter than reporting just simple index values. The system has been deployed in the real world and active since 2018, and we have a website showing the real-time status of the system, which is updated every 10 minutes. For the demonstration purpose, we use an additional gateway device that reads the classification results from the battery's learner and sends them to the web server. Thank you.